This is a topic on sequence. We have to first discuss what is the definition of a sequence, and the rest of the time is to be spent on explaining how you would calculate the so-called limit of the sequence. The first thing we want to talk about is the definition of sequence. A sequence is nothing more than just a list of numbers. The important thing that you know is the terminology of the sequence. A sequence is usually denoted with this notation. So you have an curly bracket with the symbol AN. Each of the AN is actually a collection of terms in the sequence. So each of these AN is called the terms. For example, you have A1, A2, A3, up to A infinity. Usually, each of the terms here is called a term. So for example, you have the A1 term in the sequence, the A2 terms in the sequence, the AN term in the sequence. In each terms, the N that appears in the subscript is called the index. So you have, say, for example, A subscript 1, A subscript 2, A subscript 3. Here, the subscript in the term A1 is 1. Here, the subscript 2 is the index n equals to 2. And here, A3, the subscript 3 refers to the third term in the sequence. So when we talk about the sequence, we refer to this terminology, the sequence, which is written as the curly bracket containing AN, and each AN is called a term, and the subscript N here is called the index. So these are the terminology that is been defined in these slides. Therefore, before we begin talking about sequence, you have to understand the naming or the terminology used to describe an sequence. Then we usually represent an sequence AN using a formula that relates the AN terms to the index of n. For example, you write AN equals to 2n. So that the sequence that is formed by AN equals to 2n is a so-called a list of number, which is like 2, 4, 6, 8, 10, etc. up to infinity. In this case, the sequence n usually lasts from 1, it begins from 1, and it will extend to infinity. Such a sequence is called an infinite sequence. You can describe the numerical behaviors or the trend of a sequence if you know how the terms an is expressed in terms of n. So these are the example of sequence. The term of the sequence an is given by the square root of n. Therefore, the sequence is expressed as a list of number. The first number in the sequence is square root of 1. The second term is square root of 2, etc. And the n term in the sequence is just square root of n. And the numbers of terms in the sequence last to infinity. So as long as you know how the terms in the sequence is expressed in terms of n, then you can write down the elements or the terms in the sequence one by one. Now, sometimes I call each of the term in the sequence as the term, or sometimes I usually refer them to element as well. So when I say elements in the sequence, I mean the terms in a sequence. So the sequence can be expressed in many forms. So these are the example of sequence A, sequence B, sequence C, and sequence D. Once the expressions of the terms of the sequence is given, you should be able to write down the terms in the sequence. For example, if you're given sequence D, equals to minus 1 raised to the power of n plus 1, then you know that the first sequence corresponds to the index n equals to 1. When n equals to 1, d1 is positive 1 and d2 is negative 1. The third term, n equals to 3, corresponds to the positive 1, etc. So up to this point, it is understood that anytime when a sequence is given in the form of an equals to a function of n, or bn as a function of n, or cn as a function of n, then you will be able to write down the all the terms in the sequence beginning from the first term, etc. You can also represent the sequence in the forms of an an versus an axis, like what is shown here as an example for the sequence an equals to the square root of n. So you know that when n, the terms, one of the terms, the index of the sequence start from 1, the values of a1 is 1, the term a2 is this, the term a3 is this number, term a4, term a5, and you represent the values of an as the value that lies on the vertical axis. You can also represent the sequence along these directions, where you jot down the values of the term an as a distance from the origin. Right, so this is the term a1 that is this far away from the origin, then a2 is this far away from the origin. So a2 is further from the origin than a1, therefore the values of a2 is larger than a1, and the first term a1 has a value of 1. So this is another example. If you have a sequence of 1 over n, you can represent the sequence of an in this very simple manner form. And you can also represent the values of an on the horizontal axis. You find that the a1 is equal to 1. The higher terms in the sequence, a2, etc., get closer and closer to the 0. So there are two ways of visualizing the sequence in the forms of a graph. Either the graph of an versus n, or the graph of a horizontal axis, where you label the values of an as point on the horizontal axis at the distance of some distance away from 0. The idea of representing the sequence in this graphical manner is to visualize how the terms in the sequence behave. For example, if you look at the first term here, the an term in this example, where an is square root of n, you find that the larger the n, the larger an is. Right? So when n increases, the values of an increases. So in this sense, you can sort of like loosely relate a sequence to a function. For functions, what you have is the values of the function represents a, whereas x represents the index n. However, for a sequence, the n can take only a positive integer starting from 1, and then an somehow represents the values of the function. For a function, the x can take any continuous value, and in principle, it can be defined for all real number, -1, 0, or +1. But you can imagine that if you restrict only x to integer number 1, 2, 3, 4, then the values of the function f at only integer, a positive integer of n, the values of fn then can represent the values of the term an. So there is a loose relationship between a series, a sequence, and a function. Here, the functions is written as f of x, and the values of f depend on the independent variable x, whereas in the sequence, the values of the function, so-called function, is given by the values of an, and the index n here plays the role of x in the function. But the n, that is the index that appears in the sequence, is only beginning from +1. So from the graph of the sequence, you can roughly develop a kind of feeling whether the sequence will converge or will diverge. So for example, you look at sequence A1, it will actually get smaller and smaller as n get smaller. So in this sense, you can sort of like roughly associate the sequence of an equals to 1 over n to the function of fx equals to 1 over x. Roughly, you would then realize that when you make n to infinity, then the behaviors of the sequence an will behave like the function f equals to 1 over x. That is, when n goes to infinity, the sequence an will also goes to 0. But for the case of the an, it's slightly different. Usually we don't have this kind of function because most of the time the function sign is consistently positive or consistently negative. But here in the case of the alternate function, so-called, the sign of the sequence can alter when n change from odd to even, from even to odd. But overall, the magnitude of the sequence an becomes smaller and smaller as an increases to infinity. So in this sense, the an does not really look like a function, but the magnitude of an actually behave like a function of 1 over x. So we call this kind of sequence, well, we call this kind of sequence as an alternating sequence. Up to this point of page 5, we have just gone through a few examples of sequence. But the idea here is to let you realize that if you are given a sequence of an, you can talk about the convergence of a sequence. That is the limit of a sequence. The limit of a sequence is a number of L that fulfill these definitions. So if such a values of L exists, then we said the sequence of an converge to L. So this is a symbol that is written down to represent the limit of a sequence. So basically the limit of the sequence can be easily understood from this figure 11.2. That is, it says if the sequence has a limit of L, that must mean that for any values of n that you give, as long as the small n, that is the index of n, is larger than the n, then the values of the sequence an must always be sandwiched between L plus epsilon and L minus epsilon. So there always exists such and values of n for any values of positive epsilon. So the idea of the limit of a sequence is very, very related or very similar to the definitions of a function. You can also have the definitions of a functions that is converging. Here you also have the definition of a sequence that is converges. So if a sequence converges to L, then we say L is the limit of the sequence. If there exists no such values of L, then we say the sequence does not converge. So this is the formal definitions of the convergence or divergence of an sequence. The idea of the limit of the sequence is very similar to the definitions for the limit of a function. So anyway, when we are given a sequence, you can always ask the questions of whether the sequence diverges or converges. Okay, so this is the definitions of a sequence that is diverges to infinity. Here is the definitions of a sequence that converge. So if a sequence converge, then this is the definition that exists in L, for which when n is larger than certain values of n, then the an is always sandwiched between this L plus epsilon and L minus epsilon. Likewise, you also have the definitions for the divergence of a sequence. That is, a sequence is said to diverge to infinity if this definition occurs. Basically, it means for whatever values of m that you can think of, any positive number, then if the sequence diverges, it means that whenever n is larger than some number capital N, as long as you have n values of m, which is a large, arbitrary large positive value, the divergence of the sequence means there always exists values of n, such that when the n is larger than the capital N, the an is always larger than m. So that is the definitions of the divergence of an sequence to infinity. Okay, so let me repeat it again. The divergence of an sequence to infinity, it means whenever a positive number m is given, you can always find a capital N such that whenever the small n or the index of n is larger than n, the values of the sequence of an is always larger than m. So whatever m you give, you can always find existence of the capital N in which this statement is true. So that would means a functions or that would means an sequence is diverging to positive infinity. Same concept also applies to a sequence that diverges to negative infinity. So up to this point, I have been roughly going through the definitions of the convergence of a sequence and the divergence of a sequence to infinity. We need to have these definitions in order to go through the next slides. So the next slide is this. It's a theorem that contains 5 sets of rules that tells you if you have a sequence an which have a limit of a and sequence of b that have limit of b, then when you combine the two sequences together to form new sequences, then the limit of the new sequences obeys this rule. So it says that if you have an sequence and you have bn sequence, then you can combine a new sequence, which is an plus bn, that is term by term in the n, you can form a new sequence Cn, where each term in the Cn is the sum of the term an and bn. So here the Cn is a new sequence, which is formed from sequence A and B. And if you know what is the sequence limit for A, the sequence limit for B, then the limit of the sequence Cn obeys this rule, that is the sum of the limit of sequence A and the limit of the sequence B. Likewise, if you form a new sequence of Cn, which is defined to be the difference between the sequence an and bn, then the limit of this new sequence obeys this difference rule. Likewise, for the product of a new sequence which is formed from multiplying the term an and bn, then the limit of the new sequence an times bn is just the product of the respective limit. You can also have this constant multiply rule and quotient rule. Therefore, these are the very simple theorems that applies to the limit of sequence. At a glance, the theorem 1 that applies to the limits of the sequence are very much similar to the theorems that applies to the limits of two functions, which we have seen in previous chapter. So up to this point, we have understood that if the sequence has a limit, then these are the rules that applies to the limit of the sequence. And we have also been explained briefly what is the definitions of the limit of a sequence. So up to this point, you should understand that if I give you a sequence, you should be able to tell me whether the sequence has a limit or not. Then these are the rules that applies to the sequence. to the limit of the sequence. For example, example 3, you are asked to find out what is the limit of the sequence minus 1 over n. So let me write down these slides on a separate table so that I can explain the calculation of that. It should be actually quite simple to understand. Okay, I have to relaunch my whiteboard. Seems like there is some problem with the whiteboard. So you are asked to find out what is the limit of a sequence. You are asked for the limit of the sequence, which is written as this, where the an, that is the expression of the term in the sequence in the example 3a1, is written as minus 1 over n, right? So you're asked to find what is the sequence, what is the limit of this sequence. So the idea is actually very simple. The idea is that the limit of this sequence an, which is the limit of n goes to infinity of minus 1 over n, according to the theorem, of the product rule, constant multiply rule. Here you can assume that these terms is the product of minus 1 times 1 over n. Therefore, these terms, according to the constant multiply rule, can be then expressed as the product of minus 1 times the limit of n goes to infinity 1 over n. So when I write down this line of equation from the previous line, I am making use of rule number 4, which is the constant multiply rule, in which the k is the minus 1 here. Therefore, this is just simply equals to minus 1 multiplied with the limit of 1 over n when n goes to infinity. So that is simply equals to 0, 1 times 0, which is 0. So the fact that I'm writing down this is making use of theorem item 4 in theorem 1, which may seem to be very obvious, but you can only do that with theorem 4, with theorem 1, item 4 given to you. So same thing could also apply to say example 5b. You have a limit of you're asked to find the limit of the sequence n minus 1 over n, where n goes to infinity. So to do these questions, again, I'm going to show you explicitly the step-by-step procedure. You're asked to find the limit of n sequence. Here, the sequence an is expressed by n minus 1 over n. So the limit of the sequence is written as n goes to infinity for n. So what is this? So to do these questions, you just write down the calculations for n minus 1 over n. Then you just do some rearrangement in expressions of this. What you do is that you will try to express this expression n minus 1 over n in the form of 1 over n. We try to make it to be always expressed in terms of 1 over n as much as possible. So what you do is just you simply pull out the factor of n from this expression, then No, you don't pull out. What you do here is that you just rewrite this as 1 minus 1 over n. Right, so n minus 1 over n is just n over n minus 1 over n, which is just 1 minus 1 over n. So from here to here, nothing fancy has occurred. It's just a rearrangement of the expression using some simple algebra. Now we have a difference of two terms. The limit of n goes to infinity for this term minus this term. Therefore, this is written as limit of n to infinity 1 minus or plus limit n goes to infinity minus 1 over n. And in example A, we have already seen that this goes to 0. And here, the limit of 1 when n goes to infinity is still 1. So when I write down these equations, number 2, where I split the limit into the sum of two limits of rule, okay? So I just split the sum of two terms into the sum of the two limits separately. So that is how I perform the calculation for example B. Likewise, for example C, you pull out the 5 as the constant. Then what is left is n squared in the limit. So the calculation could then be easily obtained. Now let me try to write this again for you. The questions of C is to calculate the term of n squared when n goes to infinity. So the first thing you do is to apply the product rule, the constant product rule, or you pull out the 5 of the constant product rule. Then what is left is 1 over n squared. And then this means a product of two terms. So the limit of n to infinity for 1 over n squared is considered as the product of 1 over n and 1 over n. And according to the product rule, this can be then broken down into the limit of two terms. So when this is written down, I am making use of the product rule. Okay, in the product rule number 3, you have a product of an and bn. Then you can break them into two separate limits. Here a is 1 over n, b is also 1 over n. Therefore, you have 5 times 0 is also 0. So finally, you get a number, which is the result is 0. However, the steps have to be carried out step by steps, following the set of rules that is specified in theorem 1. So these are very simple example C, and let us look at example D. Example D also is a little bit complicated, but not as complicated. So let me write down the example 7 on my whiteboard. So this is the example D. You are asked to find the limit of the sequence 4 minus 7 and 6 over n power 6 plus 3. Now mind you, when you are calculating the limit of this, it's very similar to the calculations of the limit of a function, except here the function is replaced by the sequence. Instead of x, you are dealing with the index n. So the way how you do this is try to express this in the form of 1 over n as much as possible. So what you do is you pull out the factor of 1 over n squared. Then what is left is 4 over n power 6 minus 7 over 1 over n power 6, 1 plus 3 over n power 6. And the limit of n power 6, 1 over n power 6 for here 1 over n power 6 will become 0 when n goes to infinity. The term of 1 over n power 6 will get cancelled off here. So when you get that, then what's left is the limit of n going to infinity of 4 over n power 6 minus 7, 1 plus 3 over n power 6. So now you have the ratio of two terms. So according to the theorem that we just mentioned, the quotient rules, it says if you have the ratio of two sequence, then this is what you get, a over b. So you can then write down this as the ratio of the limit of the numerator over the limit of n goes to infinity, 1 plus 3 over n power 6. And this term is written down from here by using the quotient rule that I mentioned. So then you proceed on. This will be just giving you 0. This will be just giving you 0. And you have minus 7 over 1. So that is the limit of the sequence. So up to this point, we have learned a few examples of applying the theorem 1. And finally, we are able to work out the limit of these few example sequence.